Hey everybody. So as you can see, I'm going to do a couple of examples using L'Hopital's rule, but a couple of examples where it's not quite as obvious that L'Hopital's rule applies. Remember, L'Hopital's rule is specifically about quotients of functions, right? If you have, let's just write it this way, if we have the limit as x goes to a, it could also be infinite of the quotient of functions, over g of x. If this is indeterminate, I think I'm going to misspell this. And so that means the limit is 0 over 0 or plus or minus infinity over plus or minus infinity. Then we can say the limit, this limit is equal to the limit of the derivatives. Okay, so this is the only thing it says, right? It doesn't tell us that all indeterminate forms can we just take derivatives and take the limit, right? It specifically says quotient, so that's all that it applies to. However, we can sometimes manipulate things until they're in this form, right? As long as we can get them in this form, we're okay. So let's start with this example, okay? So the first thing to note is you've got if you look at these limits, the x squared square root, that thing in the square root, when we get really big, is about x, as is the other thing in the square root, right? The 5x and the minus 4x don't really do much when you've got a billion. A billion squared is much bigger than 5 billion. A billion squared is much bigger than 4 billion, right? So those little extra things that mean a lot where small values of x mean very little when we're out to large numbers, right? And so both of these are getting very, very big, very large, and we end up with an infinite limit, infinity minus infinity specifically, which doesn't tell us anything. We don't know, right? One's trying to make this very, very positive. One's trying to make this very, very negative. We don't know what happens. One of them may win and it becomes very positive or very negative. They might cancel each other out, let's say, and land on 0. They might land on some number in some other number than 0, and they might just do something weird that causes there to be no limit. We don't really know just by looking. So, and we can't apply L'Hopital's rule because L'Hopital's rule doesn't say anything. There's nothing in this rule about differences. So what we need to do is see if we can rewrite this thing in a more convenient way. And we're going to try a trick that we've seen in other contexts and see if it helps us out here. And so what I'm going to try to do, we don't even need a new. I'm going to multiply this thing by 1. Okay, so I'm going to think of this first of all as a fraction over 1. That's not changing anything about it, so I'm allowed to do this. And then I'm going to multiply it by 1. But the way in which I'm going to multiply it by 1 is by multiplying by the radical conjugate over itself. Okay, this fraction is totally legitimate. If x were equal to 0, it doesn't exist, but we're looking out at towards infinity, a large number. So we're far away from 0. So in the place we care about, the 0 in the denominator won't happen. Okay, because otherwise, if x is not 0, everything, these square roots are going to be positive, right? Once we're up to large x's. Bigger than 4, I guess we'll always have things greater than 0 in here. Okay, so let's see what happens with this algebra. So we get in the numerator, right? We've seen this before. When these two multiply together, the square roots are gone. We're taking that thing and squaring it. We get these two, which gets rid of the square root, but also we have a negative. The cross terms are opposites to each other. So there's this term here and this term here. They have the same factors, except one of them has a negative factor, so they cancel out. So those are all gone. And then our denominator, we're just going to leave as is. Okay. So there is our there is our new form, right? So this is an equivalent expression. We haven't changed the function that we're taking the limit of. We've just written it in a different way that's at least equivalent for the values of x that we care about. Okay, let's do a little algebra in that numerator to simplify things. We've got an x squared. We'll have a negative x squared from that, distributing that negative, so that's gone. And then we'll have a 5x and a positive 4x. So we end up with 9x over x squared plus 5x plus x squared minus 4x. Okay. And now we can use one of the lessons we learned from taking limits at infinity, where we look at the denominator. We've got something like a rational function, and in the denominator, we have these squared x terms under the radical. And so the idea was we multiply by 1 over the highest power of x in the denominator, but in this case, the x squared is under a radical, so the highest power of x is just x. So I'm going to multiply the numerator and the denominator by 1 over x. Again, I'm not changing anything because x is certainly greater than 0, and so this is just a 1. So we have the same function. We're just going to be looking at it from a different perspective. So the numerator, 1 over x times 9x is just 9. In the denominator, right, for each of these radicals, we're going to use that 1 over x is the same as 1 over the square root of 1 over x squared. Right, this works because x is positive. We've seen before that if x is negative, we have to pick up a negative sign. And then when we multiply this by our radicals, we can bring them inside, right? We can bring this inside like that using, right? So whatever, depending on which one of the radicals we're multiplying by, we bring in a 1 over x squared. So when we bring it inside this first one, we'll have a 1 over x squared multiplied by to these two terms, we get 1 plus 5 over x. And then when we bring it inside this term, we get 1 minus 4 over x. Okay. And now we can take the limit of the top and the limit of the bottom. In the numerator, the limit of 9 is just 9. In the denominator, we'll take the limits, we'll split it over this sum, then we'll take it inside the radical. Inside the radical, the limit of 1 is just 1. The limit as x goes to infinity of 5 over x is 0. Our other radical, we get 1 minus 0. So we've got 9 over the square root of 1 plus the square root of 1. The square root of 1 is, of course, 1. So we've got 9 over 2. And there's our limit, right? We didn't even end up using L'Hopital's rule, right? I threw this into L'Hopital's rule examples because these indeterminate forms encourage us to think about L'Hopital's rule, but it doesn't actually end up applying here. There's a way to do it with L'Hopital's rule. I'll leave it up to you. You can factor out, at least I think there is. I haven't actually done this before, but somebody mentioned it, and I'll leave it up to you to try. You can factor an x squared out of these two radicals and pull that out front, and you can write this as a quotient of two things that go to 0, I believe, and take derivatives. If I have time, I'll try to make one showing that method where you could use L'Hopital's rule, but we didn't end up having to do that here, right? And so what we see is, in the end, this fight between one trying to make it really large and one trying to make it really small ends in, I guess, a tie. We're in the middle. We're at 9/2, and so for whatever reason, that's how this battle plays out. We end up with 4.5 as the limit. This expression gets closer and closer to the number 9/2. Okay, let's do one more. And this one's a little bit of an application that's kind of neat to see. And this comes from economics. This is probably something you've seen before. This is a function that gives us, let's call it P of t, tells us the amount of money in an account after t years. Right? And so if you're earning interest, this can be written this way, P naught. I'll explain what each piece of this is in 1 second. 1 plus R over N to the NT. So here, P naught is the initial investment or initial principal. I think that's the word they use, why they You see a P a lot. And then R is your interest rate. N is the number of times you're compounding per year. All right, and then T, of course, is the number of years. Right, that compounding per year just means this. Let's say you're earning 5% interest. If you have $100 in there, let's say they're compounding it. Did I say this already? Twice a year. Halfway through the year, you would get 2.5%. So you have $100, 2.5% would be $250. You now have $102.50. And then at the end of the year, you get another 2.5%, right, for your total of 5% interest for the year, except that second 2.5% gives you 2.5% of your original 100, so you get another 250, but you also get 2.5% of that 250 you got halfway through the year. So what, that's like 6 cents or something like that. You get a little bit extra. So the next time you'll get 256 or something like that, right? Which is a little, but over years, this kind of compounding can make a big difference versus just getting the 5% at the end of the year, right? If you just got 5% at the end of the year, you have $5. In this compounding twice a year, you get, what did I just say? Oh, $5 and some change, 6 cents or so, right? And then the next year, it'll be a little bit more and so on. And this is how interest starts to accrue and become this great amount of money, right? Well, you can compound many different times per year, right? So monthly is one thing you could do, weekly, daily. An interesting question to ask is, what if you were constantly compounding? Meaning the number of times you're compounding per year is infinite, right? You're not saying every minute or every second. It's just always compounding, always growing. That's a weird thing to think about, but we can answer this kind of question with limits. We could talk about compounding I don't know what letters I just put in there. Compounding continuously. We can think about this as n going to infinity, right? The number of times per year that you compound is, sorry, I just tripped, is infinite or is approaching infinity. And let's see what's happening to this function. It's surprising, perhaps it doesn't just give you infinite money, it sort of lands on something in the middle. So let's take a look at that. In other words, what we want to do is take the limit as x goes to infinity. Sorry, not x. There's not even an x in this problem. We want to take the limit as n goes to infinity of this p naught 1 plus r over n to the nt. Okay, so my first step is I'm going to just take p naught out. Right, it's a constant. It's how much money you put in at the beginning. This is one of our limit laws. It does not get affected by that limit, and so we've got a little bit simplified of a problem. So let's now just examine this piece, right? I don't need to have this constant floating around. We'll put it all in at the end. So now I want to consider the limit as n goes to infinity of 1 plus r over n to the nt. Okay, now let's think about what's happening here. N is growing large. So we're thinking of r as a constant and t as a constant, right? T is the number of years. So what we're going to end up with is something that tells us if we compounded an infinite number of times per year, how much, we'll get a function that tells us how much we would get after t years, what our interest would be, okay? So as n gets large, the r over n is going towards 0. And so the parenthetical is becoming a 1. It's getting really, really close to 1, right? Meanwhile, nt is getting really, really large. It doesn't matter what value t has, as n gets large, for any given number of years, n's getting larger and larger and larger. So you're taking numbers like 1.00000001 and multiplying them by themselves, which isn't very big, except if you do it a lot of times, it starts to get big. So we've got this fight again, right? We can write this very inappropriately as 1 to the infinity. This is indeterminate because we're not actually multiplying 1 by itself an infinite number of times. which you could argue is just 1 because it's never going to change, right? Or if you have a good definition of what it means to multiply an infinite number of times, 1 would be a good argument. But that's not what's happening here. We're multiplying numbers close to 1 lots and lots of times by themselves. And then we're increasing how many times we multiply them by themselves, while at the same time decreasing their distance from 1. And this pull between these two things isn't obvious. It's not obvious who's going to win this battle, okay? One's trying to make it really big, the infinite exponent. One's trying to keep it at 1 by making that base close to 1. So let's dig into this a little bit. We're going to use a little, let's call it algebraic trickery here. And I'm going to rewrite this expression. I'll do my scratch work over here. 1 plus r over n to the nt as e to the natural log of 1 plus r over n to the nt, which is equal to e to the nt. So to be clear, that exponent is inside the natural log's argument, which means we can take that exponent down. We have the natural log of 1 plus r over n. Okay, so that's what our new limit is. The limit of e to the nt times the natural log of 1 plus r over n. And then we're going to use one of our limit laws that lets us pass this limit into the exponent here, because that there's limit laws about compositions of continuous functions. There's some domain considerations, but everything works out here. We've got the exponential is continuous everywhere. So now let's focus on this limit up here. Okay, so now I'm just looking at the limit in that exponent. We've got the limit as n goes to infinity of nt natural log 1 plus r over n. So this first term, well here, let's just write it as the product of two limits. This is a limit law. The limit as n goes to infinity of the natural log of 1 plus r over n, okay? This first term, n times t, for any given value of t, n's gonna go to infinity. And t is gonna go to infinity, right? And as long as t is positive, but it is. It's a number of years since you've invested. So we've got an infinite limit. Let's write something somewhat incorrect again, or at least maybe misleading. The second limit is the natural log of 1 plus r over n. R over n goes to 0, natural log of 1 is 0. So we end up with something that looks like this, okay? Again, you might think to yourself, well, it doesn't matter if it's infinity, 0 times anything is 0, but that's not what's happening here. We're not multiplying 0 by anything. This second term never gets to 0. What we're saying with these symbols is that I've got one thing getting infinitely large. For every value of n, we can just keep, every time we increase that, it just keeps getting larger and it'll never stop getting larger. And we're taking these really big numbers and we're multiplying them by these other set of numbers that as we increase n, get ever smaller, get closer and closer to 0. So one part of the product, one factor is getting really, really large, one is getting really, really small. And the question is, who wins? That same battle that we saw when we first looked at this is still here. We've reformulated it a little differently. Instead of a 1 in the base and an infinity in the exponent, we've got an infinity times a 0, but we've still got the same push and pull between these two, okay? So this is an indeterminate form. It's an indeterminate form of products. L'Hopital's rule doesn't tell us what to do with an indeterminate form of products. What it tells us is what to do when we have the indeterminate quotients where the limits are 0 over 0 or infinity over infinity, plus or minus on either of those. So we can't apply L'Hopital's rule as written. However, let's acknowledge that this doesn't tell us anything. We can rewrite our limit in the following way. I'm going to keep this, so I'm going to go, let me rewrite this. I'm going to go back to this first formulation, nt natural log of 1 plus r over n. And now what I'm going to do, I'm going to leave that t alone. Natural log of 1 plus r over n. And I'm going to put that n in the denominator as an n to the negative 1. Right? The negative 1 tells me that it's the same as having an n in the numerator, which is what we had. So algebraically, these are equivalent, right? Once again, reminding ourselves that this doesn't work if n can equal 0, but we're looking at large values of n. So 0 is not something we have to worry about. Now, we've got something rather nice. Because in the numerator, the natural log of 1 plus r over n, as we set up here, goes to 0. And in the denominator, we've got n to the negative 1, or 1 over n. As n gets large, that also goes to 0. So now I have the 0 over 0 indeterminate form, and L'Hopital's rule tells me exactly what to do. L'Hopital's rule, here's my little mark for that, says I need to take the derivative in the numerator and the denominator. So let's take those derivatives. This is the derivative with respect to n. That's the thing we're letting vary right now. So I'm going to take the derivative of ddn of t times the natural log of 1 plus r over n. Okay, so I'm going to do a little cheat here. I'm going to think about the inside of here in two ways. 1 plus r over n is the same as n plus r over n. So the first part of my derivative, well, the t will just carry through. That's a constant as far as n is concerned. The derivative t doesn't change as we change n. The first part of my derivative, we've got a chain rule, is to take 1 over the argument of natural log. I don't like this 1 plus r over n to do 1 over, but if I think of 1 plus r over n as this thing, n plus r over n, 1 over is just its reciprocal. So we end up with n over n plus r. But now we have to multiply this by the derivative of the inside. And here's my little cheat. Now, instead of using this formulation, I'm going to go back to the original one because that's an easier thing to take the derivative of. That's r times n to the negative 1 is going to be negative r n to the negative 2. Okay, so because they're the same thing, I can do this. I can choose which one to use, whichever one's most convenient for me at either time. You don't have to do that. You can use one formulation and just take the derivative as it is one way, but this seemed a little bit easier to me. So what do we end up with in the numerator is t times n over n plus r. We've got negative r n to the negative 2. In the denominator, I've got negative n to the negative 2. And now notice the negative n to the negative 2 is going to cancel with that factor, right? Those are the same thing, one in the numerator, one in the denominator. They cancel out, the negatives cancel. So let's see what we have now. It's getting a little messy. Let's clean up a little bit. I've got this r sitting in here I don't want to miss. So I'm going to just pull that next to the t. Those are constants. And I've got n over n plus r. Now, we're taking a limit as n goes to infinity. RT is like a constant. They don't change, right? For a given number of years and a given interest rate, we're looking at what happens as we increase n. So those are given, they're stagnant. We've got a polynomial here, a rational function, excuse me, where n is the variable, and the degree of each of the polynomials in our rational function and numerator and denominator is the same. They're both linear. They both have degree 1. And we know that the limit of these kind of rational functions is just the quotient of the coefficients of their leading terms. They both have 1. So the limit of that piece of it is just 1, right? In other words, n over n plus r as n gets big is basically 1, because however big r is, when n is a trillion, it doesn't really matter. We've got more or less n over n. And so in the end, this limit is just RT. Okay. All right, let's put it all together now. So this thing that we just computed, RT, that was the result. That was what this limit was. Okay. This limit was in this numerator this exponent of e. So this became e to the RT, right? So that thing that we just found to be RT now goes in there. Now moving back up, this thing, this e to the RT was the answer to this question, which is everything in the red box. And so that is, we have our P naught and the red box is replaced with RT. In other words, we're all together, our function becomes this. If you want to know how much, if you're continuously compounding interest, meaning every moment of every day for a year, you're always just grabbing your interest, putting it back into your total, and now it gets interest applied to it. The way it works out is this compounding function somehow has an e locked into it when we go to infinity, right? Which is a pretty neat idea. And so this is a function that you can use if you have 6% compounding continuously and you want to know how much you're going to have after 10 years. It's not going to be 6% each year. It's going to be something a little higher than 6% because at each moment of every day you're getting a little bit of interest in, and then that little extra money now gets interest in it. And so by the end of the year, you'll get a little bit extra, right? You could figure that out by putting e to the putting r of putting r as 6% or whatever you want to figure out in there and seeing how much you'd have left after 1 year. Okay. The last thing I'll say about this, and this I'll leave as a problem for you, this is related to an interesting limit. The limit as x goes to infinity, 1 plus 1 over x to the x is equal to e. In fact, this is one way you can define the number e, is the number that is the limit of this function, right? And so you might notice if you play around a little bit how you could take this limit using a very similar method that I used here and see that interesting definition. Okay, thanks everybody. That will do it for this one. I will see you next time.